Welcome to the Chemistry, Biology and Math Revision Hub. Today we are doing the Pearson Edexcel International A-Level Chemistry Unit 5 for June 2024. Let's begin with the first question. In question 1, what color is vanadium 3 in aqueous solution? Vanadium 3 is green, so the answer should be B. And next, an oxide of vanadium is the catalyst in one step of the contact process for the manufacture of sulfuric acid. Which reaction involves the vanadium oxide catalyst, and how does the oxidation number change during the process? So in this reaction, sulfur dioxide will react with vanadium 5 to form sulfur trioxide and then vanadium 4, and the remaining vanadium 4 reacts with half oxygen to produce vanadium 5. This is a reduction for vanadium and this is oxidation. So the answer should be C, from 5 to 4 and then to 5. In question 3, an equation for the reaction of iron sulfate with potassium manganate 7 is shown. So this is the equation for the reaction. They say, which shows the changes in oxidation states for iron and manganese. Now in here, manganese is +7. Here iron is +2. This is going to be reduced to +2 and that will be oxidized to +3. So the answer for iron from 2 to 3 and manganese from 7 to 2, A should be the answer. In part B, a 25 cm³ sample of iron sulfate dissolved in acid required 22.5 cm³ of 0.1 mole per decimeter cubed potassium manganate 7 for complete reaction. What is the concentration of iron sulfate solution? So here I'm going to use the information for potassium manganate to calculate the moles, which should be the concentration times the volume. I multiplied by that to convert it to decimeters cubed, and these are the number of moles I got. Then when we go back here, if I know the moles of this, the ratio is 2 to 10, which is basically 1 to 5. So to get the moles of this, I multiply the moles here by 5, meaning moles of iron sulfate should be 5 times the moles of potassium manganate 7, giving us that. And then finally, the concentration of iron sulfate should be number of moles divided by the volume. Remember that volume is 25, so the answer is 0.45 mole per decimeter cubed, and so C is the answer. In question 4, the EMF, E theta for the cell of the cell made up of the copper manganese half cells is measured under standard conditions. The voltmeter used has a measurement uncertainty of 0.5%. What is the highest EMF that could be measured in this experiment? So we have to use the data booklet. Using the data booklet, I got the equation for copper and that for manganese with their corresponding E theta values. And I calculated the E theta for the cell. Since this is more positive, that is more negative, this is going to be oxidized as that is reduced. So the E theta for the cell should be that minus this one. Since there is a measurement uncertainty of 0.5, it means 0.5 divided by 100 times this value here gives us the value we should add or subtract in order to get the minimum or maximum. So adding it to get the maximum, so 2.71 plus that gave me a value closer to 2.72, and so B should be the answer. In question 5, which is the diagram for the cell made up of nickel and zinc half cells that give a positive value of E theta for the cell. Again here, using the data booklet, I gather two equations, one for nickel, the other for zinc. And we realize this is more negative, so this should be oxidized as the other is reduced. So we begin with zinc, and then we put a separator because this is solid and that is aqueous, so we should have a vertical separator. And then these to represent the salt bridge. Then the other side where reduction is going to occur, we begin with the most oxidized version, which is going to be nickel 2, becoming nickel 1 as reduction takes place. So the answer should be A. In question 6, which graph shows the relationship between the E theta plotted on the x-axis and the S total on the y-axis for any electrochemical cell? We know that the S total is proportional to E theta for the cell, so any graph showing a positive correlation or a positive relationship is going to be correct. And if we compare all the possible results here, we can see this is suitable, so the answer should be A. It shows a positive direct relationship between the two, so that should be the answer. In question 7, which type of data is used as evidence for the structure or stability of the benzene ring? We use infrared spectroscopy. We also use thermochemical data like enthalpy change of hydrogenation, And we also use X-ray diffraction data, but we do not use mass spectrometry, so B is the answer. In question 8, the formation of nitrobenzene requires benzene and concentrated nitric acid and sulfuric acid, which is the equation for the reaction to form the electrophile. The electrophile should be an O2+, and there is also formation of this ion, but the sulfuric acid is going to donate its hydrogen to form this, so the answer is going to be B. In question 9, phenol reacts with bromine to form 2,4,6-tribromophenol. As we can see the equation, they say what is the percentage atom economy by mass for the formation of 2,4,6-tribromophenol? Since this is the desired product, the percentage atom economy should be the molar mass contribution from this divided by the total times 100. So it's going to be this, divide by that plus 3 times that because these are 3. And then multiply by 100, and I got 57.7%, which makes B the answer. Then in part B, they say when 5 grams of phenol was reacted and purified, the percentage yield of 2,4,6-tribromophenol was 76.8%. What mass of purified 2,4,6-tribromophenol was formed? So here they're looking for the actual yield, giving the percentage yield. So I began by finding the moles of phenol because we're given the mass, so moles should be the mass. Divide by the molar mass. The molar mass was given here, which is 94. So I got those. And since the mole ratio is going to be 1:1, the product theoretical moles are going to be exactly the same. You can see the ratio is 1:1. So it's the same number of moles. And then the theoretical yield, which should be the mass, is going to be number of moles, which we have here, times the molar mass of the product, which is 330.7, giving us 17.59 grams. And so finally, the percentage yield should equal to actual divided by the theoretical times 100, and making actual the subject, I got 13.5 grams, which makes B my answer. In question 10, aspartic acid is a naturally occurring amino acid. Which form of aspartic acid is formed at pH 12? pH 12 is alkaline, and so we expect the hydrogen ions to be lost from the carboxylic side. So since we have 2 carboxylic sides, both are going to lose the H+, creating this, and so C is going to be the answer. Then in part B, they say glutamine is shown, which we see here. It has 1 carboxylic part, and then we have this amine part. They say which is a correct structure when aspartic acid forms a dipeptide with glutamine. I wrote the 2 structures here that have to combine in order to produce a suitable dipeptide. And if we look at A, there is no way it forms this structure when these 2 are combined because the combination did not occur appropriately. Among all these 4, it's only D that created the proper linkages in order to form the dipeptide, and so D is my answer. In part B, what is the maximum number of chiral centers in the dipeptide in B1? So since this is my dipeptide, the chiral centers, I see this carbon here and that carbon there, so they are 2 chiral centers. This is not because there is a double bond here. This has 2 hydrogens, this has a double bond, and this has 2 hydrogens, a double bond, so it's only this and that. In question 11, a student prepared a sample of aspirin. The equation for the reaction is shown here. So they said the aspirin was recrystallized using an ethanol water mixture as the solvent. The student determined its melting temperature using the apparatus shown. We can see the setup. Then they say the student's sample melted over a range of 8 degrees starting 125 degrees Celsius. The published melting temperature of pure aspirin is 135, which is a suitable liquid to go in the beaker. The liquid in the beaker should have a higher boiling point than the melting point of the solid, so it should be mineral oil. Then they say which is likely to be the main impurity in the sample of aspirin. So since we used an ethanol water mixture, anything that is not soluble in this mixture, when cooling occurs, is going to be an impurity because it's going to crystallize along with the solids. So I chose 2-hydroxybenzoic acid because of course you see it has a bigger or longer R group. Its solubility in the water ethanol mixture is not that great. So basically it dissolves better in ethanol, but in the water ethanol mixture is not that great. And if the temperature decreases, then its solubility is going to decrease as well. So D is going to be the answer. In question 12, Wigner's reagents are very useful for increasing the length of the carbon chain of organic compounds. Which metal is involved in the formation of a Grignard's reagent? This should be magnesium. So the answer is C. Then in part B, what best describes the role of Grignard's reagents in increasing the length of a carbon chain? Because it has some halogens like Br, it's going to act as a nucleophile. So the answer should be C. Then question 13, propanoyl chloride and N-methylpropylamine react to form an amide and hydrogen chloride. The structures for the reactants are shown here. They say what is the structure of the amide formed. Now in this case, I try to draw the mechanism. There is a lone pair here, it comes here. Of course, I skipped this part where this bond breaks to give the electrons there and then returning, then Cl goes. So skipping what happens here, this is going to be number 1. Number 2, then this carbon attaches to the nitrogen. And then the hydrogen goes away, creating this as the structure. Then the hydrogen and the Cl form HCl. So we are looking for this structure here. And if you look at the possible answer, CH3, CH2, CH2, which is that, then nitrogen with this CH3 being here, and then the rest, which is that, being there. So this is the answer. And then they say if 64.3 grams of the amide is produced, what volume of HCl is formed at room temperature and pressure? Assume that stoichiometry is 1:1. 1 mole of gas occupies 24 dense meters cubed at room temperature and pressure. So I'll begin by finding the moles of the amide. From the previous question, this is what we have: 7 carbons, 15 hydrogens, 1 oxygen, and 1 nitrogen, giving us 129 gram per mole. So the mole should be the mass given divided by 129, giving us that. And this means these are going to be the moles of HCl as well. So the volume of gas should be this number of moles times the molar gas volume, giving us 11.96, which is approximately 12 decimeters cubed. And so A is the answer. Moving on to section B, question 14. They say this question is about cell reactions involving chromium. They say use your data booklet when answering this question. The first part says name the type of forward reaction that is shown in the right-hand electrode system of the data booklet. It's going to be reduction because they're gaining electrons. Then they say name the series formed when the right-hand electrode systems are placed in order most negative first. It's electrochemical series. In part B, a student set up the following apparatus to measure the standard electrode potential for the right-hand electrode system 8 in your data booklet. So we see the setup. There is hydrogen gas coming in, there is a platinum electrode, 1 mole per decimeter cubed hydrochloric acid, a salt bridge, and then parts this side. Remember, system 8, this is going to be chromium. So they say identify X and Y. X is going to be platinum. Y is 1 mole per decimeter cubed, chromium 3, and 1 mole per decimeter cubed, chromium 2. Then they say give 2 reasons why the initial reading on the voltmeter may differ from the stated value given in the data booklet. This could be if conditions are not standard or if a reaction took place. So I say the temperature may not be at standard conditions, meaning not 298, or the oxidation of chromium 2 to chromium 3 took place by oxygen in the air. Next, they say the voltmeter is removed and the cell is allowed to run for 1 hour. Explain the changes that would occur in the right-hand half cell during this time. Now for this case, I've written both equations here, and we see there is reduction and then there is oxidation. So I said in this cell, the E theta for the chromium half cell, you can see is more negative than that of the hydrogen. This is going to go this way. So chromium 2 plus is oxidized. The concentration of chromium 2 is going to decrease while that of chromium 3 increases. And we see the E theta for that reaction being positive 0.41 volts. So it's going to proceed in that manner. And then part C says, explain by calculating the E theta cell values why iron 2 is used to reduce chromium 6 to chromium 3, but zinc is used to reduce chromium 6 to chromium 2. So meaning zinc is a better reducing agent in comparison to iron 2. They send numbers chosen of the right-hand electrode systems from the data booklet. I chose 5, 8, 21, and 28, and we can see I wrote them here. You are not necessarily required to write them. So for zinc, with their corresponding E theta values, the one for chromium, iron, and the one for dichromate. So basically, dichromate 6 is going to be reduced to chromium 3. According to this, both iron 2 and zinc carry out the reduction. So let me see if I compare this one here. With zinc, we can see the E theta is positive 2.09, meaning the reaction will proceed. And then if I consider this an iron, we can see this is more negative than that. So this is going to be reduced by iron to chromium 3, and iron will be oxidized from iron 2 to iron 3. The E theta for that is positive 0.56. So both iron and zinc can reduce dichromate to chromium 3. But when we see chromium 3 to chromium 2, the E theta for zinc is more negative than that, meaning zinc is going to be a good reducing agent, and the E theta value for the cell is 0.35, a positive value, so that reaction will be feasible. But when we use iron to reduce chromium 3 to chromium 2, the E theta for the cell is minus 1.18 volts, and that means this reaction will not be feasible. So I said zinc converts dichromate 6 to chromium 3 and then to chromium 2 with E theta cell values of 2.09 volts and positive 0.35 volts respectively, and 2 converts dichromate 6 into chromium 3 with E theta cell value positive 0.56 volts. But iron 2 can't convert chromium 3 to chromium 2 because the E theta cell value for that is minus 1.18 volts. The next day says that the essential conditions required for these reactions to occur, they should be in acidic conditions. Question 15. 2,6-dichlorophenol is used for communication between ticks, small parasites that can infect animals, including humans. The compound can be synthesized in the laboratory from phenol. So they say 4-phenylsulfonic acid is formed in reaction A. This is then chlorinated. Hydrolysis of intermediate compound B removes the sulfonic acid group. So they say the reaction scheme is shown. Remember, they say there is reaction 1 where sulfonation takes place, and then chlorination, and then hydrolysis to remove the sulfonic acid group. In part A, they say the sulfonation of phenol is similar to the sulfonation of benzene, suggests the reagents required for reaction A. We need concentrated sulfuric acid, or you could say fuming sulfuric acid, as you see there. Then they say deduce the structure of the intermediate B. This is formed after sulfonation as well as chlorination, and when we look at the intended product, since there is no more chlorination, it means the sulfonic acid is going to be here and then the other two, so the answer is this one here. Then they say explain why the reaction of chlorine with phenol occurs under milder conditions than the reaction of chlorine with benzene. This is because the OH group of phenol has an OH group, which is an electron donating group. So the lone pair of electrons on oxygen in the OH group is going to overlap with the pi electrons in the ring, increasing the electron density. And so this makes the ring more susceptible to electrophilic attack, meaning even weaker electrophiles can react with it. Then in part B, an alternative synthesis of 2,6-dichlorophenol starts with compound C, which is this one here. Compound C is chlorinated and hydrolyzed, and then the carbon dioxide group is removed. This is decarboxylation to form 2,6-dichlorophenol. Other than phenol, name the functional group present in C. We have an ester group here. Then identify 3 factors that organic chemists would take into account when considering alternative methods for an organic synthesis. They can look into the atom economy, the yield, cost or availability of reagents, as well as the environmental impact or side reactions, as well as the purity and scalability. So any of these factors should be considered. In part D, the mass spectrum of 2,6-dichlorophenol is shown here. So this explains the relative intensities of peaks at mass to charge 162, 164, and 166. So these are all molecular ion peaks. So I say the mass to charge 162, 164, and 166 arise due to the isotopes of chlorine, because chlorine has chlorine 35 and 37, which exist naturally in a ratio of 3:1. With 2 chlorine atom combinations, we see the 92 plus 35, 35, we get a 162. The whole molecule here with all the 2 chlorines is equal to 92. So 92 plus 35 plus 37 gives us that, and 92 plus 2, 37 gives us that. So the relative intensities follow the binomial distribution. In this case again, if it's a 35-35, the ratio is going to be 3 over 4 times 3 over 4, which gives us that. 35-37, twice into 3 over 4 times 1 over 4, giving us that. And 37-37 is 1 over 4 times 1 over 4, giving us that. The ratio is 96:1, as we can see that. You studied this in AS chemistry. And then suggest why there is a corresponding set of peaks at mass to charge values 163, 65, and 67. These are values 1 higher than these ones, so this should be due to the M+1 peak as a result of presence of a carbon-13 isotope. In question 16, metal ions occur naturally in river water, but near industrial plants and concentrations can reach toxic levels. Wastewater from a stainless steel electropolishing plant contains dangerous concentrations of transition metal ions as aqueous complexes. Chemical precipitation can be used to remove these ions from water. Complete the equation for the reaction of a lab reagent with aqueous iron 3+ ions to produce a precipitate. Include state symbols in your answer. So this is going to react with 3 hydroxide ions or 3 sodium hydroxides to give us that, which is a solid, plus 3 water molecules. This is the deprotonation reaction. And then in part B, sodium dimethyl dithiocarbamate, which is that, can also be used to precipitate metal ions from wastewater in acidic solutions. A representation of the molecule bonding with a nickel ion is shown. We can see we have 3 ligands here, and each ligand is a bidentate ligand. The coordination number for the nickel is going to be 1, 2, 3, 4, 5, 6, so coordination number 6, and the overall charge is -1. Since here each ligand is -1 charge, and here we have -1, it means our nickel is nickel 2+. So they say complete the table. Charge on the ion is +2. The type of ligands, like we've already said, bidentate. Coordination number is 6, and the shape is octahedral. Then they say explain using a balanced equation why the formation of that dimethyl dithiocarbamate complex from an aqueous solution of nickel ion is thermodynamically feasible. State symbols are not required. So I got the nickel reacting with the 3 of the ligands we saw, and then the complex is formed and 6 water molecules. So because this is a complete ligand exchange reaction, when we look at the reactant side, we have 4 particles. The product side has a total of 7 particles, so there is an increase in the entropy of the system, and therefore it's going to be thermodynamically feasible. Then next they say when a 5 decimeter cubed sample of wastewater was treated with excess acidified sodium dimethyl dithiocarbamate, 245 milligrams of the dry precipitate was formed. Calculate the concentration in mole per decimeter cubed of nickel ions in the sample. So I began by getting the molar mass. Molar mass of the precipitate is 420.3 gram per mole. And so the mass of the precipitate is given here, but in milligrams, so I converted it to grams. And so the mass concentration of the precipitate is mass divided by volume. We have the mass here and the volume, which is that. So I got 4.9 times 10 power negative 2 gram per decimeter cubed. Now I'm going to use this mass concentration to get a molar concentration. Molar concentration should be mass concentration divided by molar mass, which is that divided by that, giving us 1.17 times 10 power negative 4 mole per decimeter cubed as the answer. In question 17, phenylglycine is an amino acid which can be synthesized from benzene. So this is the amino acid. They say the first step of the synthesis is the formation of methylbenzene from benzene and chloromethane. Draw the mechanism of this reaction. Equations for the formation of the electrophile and regeneration of the catalyst are shown. This means this is the electrophile we're going to use. So we start off by the ring, giving electrons to the electrophile, and then the electrophile attaching, and then the hydrogen displayed out with a half ring and then the positive charge inside. Then this bond breaks to return the electrons as the hydrogen goes away, creating the final product, which is methylbenzene. In part B, they say one of the steps in the synthesis is shown. So we have that. And they say explain with reference to the mechanism why this step in the reaction sequence will not produce a single isomer. So when we look at the reactant around this carbon, the shape is planar, so this nucleophile can attack from either side, forming two possible enantiomers, and since the product has a chiral carbon, those two enantiomers could be formed. So I say that nucleophile attacks the planar central carbon from either side. This results in a rhythmic mixture, two optical isomers or enantiomers, because the carbon becomes chiral. In part C, the final step in the synthesis is shown, which is this one here. So they say state the type of reaction and the reagents and conditions required. This type of reaction is hydrolysis, and the reagent is an aqueous acidic solution, just say an acid that is in aqueous solution, and then conditions we reflux. In question 18, fuel cells are an alternative to internal combustion engines and batteries for powering vehicles. A schematic diagram of a fuel cell is shown, which is what we see here. So they say explain how a fuel cell works, discussing the advantages, the disadvantages. Use the acid hydrogen fuel cell as an example, including your answer have equations for the electrode reactions and an example of another fuel suitable for use in fuel cells. E theta values and E theta for the cell are not required. So in this case, since we're using the hydrogen fuel cell, we're going to see hydrogen oxidized at the anode, and then oxygen is going to be reduced at the cathode. In this case, only hydrogen and oxygen come in, and the waste product is going to be water. So there is no production of carbon dioxide or other waste gases, and the water produced could be recycled in order to be used again. So I said, a hydrogen-oxygen fuel cell releases energy by the reaction of hydrogen with oxygen, producing only water as a waste product. In acidic conditions, hydrogen gas is oxidized at the anode, which is the negative electrode, to produce hydrogen ions and electrons. The equation is here. And then the hydrogen ions move through the electrolyte towards the cathode, meaning the positive electrode, and electrons will flow through the external circuit. In this case, they power the motor because you saw there is a motor here. As they flow through the external circuit, they will power the motor and they go towards the positive electrode. At the cathode, oxygen gas is reduced and it reacts with the hydrogen ions and the electrons to form water, and this is the equation. The hydrogen-oxygen fuel cells are environmentally friendly since they do not produce carbon dioxide like other fuel cells. Their only waste product is water and it can be reused. However, it's expensive to store and transport hydrogen gas. The cost of the catalyst like platinum could be really high, and the fact that hydrogen production often depends on fossil fuels limits its sustainability. The alternative could be methanol, used in some fuel cells. In question 19, in recent years there have been health and safety concerns over liquid tabs. These are capsules which contain concentrated liquid detergents. The soluble packaging breaks down upon contact with water during a laundry cycle to release the detergent. Some liquid tabs are small and colorful, which makes them attractive to young children who may be tempted to put them in their mouths or play with them. When moist, liquid tabs can burst in the child's hand, potentially irritating the eyes and skin. They can also dissolve quickly and may burst in the child's mouth in a very short period of time. This allows the contents to escape quickly, and if swallowed, they can cause severe breathing difficulties. In part A, identify the hazard symbol that should be displayed on the backs of liquid tabs using the ticks. We've seen, of course, it's not oxidizing, it's not flammable, and it's not an explosive. It's a health hazard, so they should be what we tick. And in part B, they say the capsule containing the detergent is often made from polyethanol and its derivatives. Draw the structure of polyethanol showing 3 repeat units. This is ethanol, and so polyethanol should be when you break the bond and put extensions, and then you continue with 1, 2, 3 repeat groups, and then extend out for continuity. Use your structure from 19b1 to calculate the percentage of hydroxyl group by mass in the polymer. So if I want, I could say there is a total of 3 hydroxyls over the total, or I could just use one of them because the ratio is the same. So if I use one of these, like I did in my calculation, So each ethanol contains CH2, CHOH, which is about 44 grams per mole. And each contains one OH group, so for OH, it's going to be 17, meaning the percentage is 17 divided by 44 times 100, which is 38.6%. Then next, explain why polyethanol is soluble in water using your answer in 19B1 and 19B2. It has a higher percentage of hydroxyl group. So I said OH groups can form hydrogen bonds with water. High percentage of OH groups increases the polarity as well as solubility. Then in part C, in liquid soap detergents, glycerol is added to the polyethanol. We say glycerol here. Give the IUPAC name of this molecule. This is going to be, we have 3 hydroxyl groups, so we can say propan 1, 2, 3, triol. Suggest one way that the properties of polyethanol will be improved by the use of glycerol apart from any effect on solubility. It could increase flexibility. Then they say glycerol is added to the polymer at 0.110% by volume. Calculate the number of moles of glycerol added to 1 ton of polyethanol. They've given us the data of densities of each. So we know density is mass over volume, and therefore volume should be mass divided by density. 1 ton is the same as 1,000 kilograms, therefore 1 million grams. So the mass should be 1 million grams divided by the density, which is 1.19, giving us this in volume. So if it's 0.11% of glycerol, it means in 8.4034 times 10 power 5 centimeters cubed, it's going to be 0.11 divided by 100 times that, giving us 924.37 centimeters cubed of glycerol. Now mass of glycerol is going to be density times volume, which is the density we have here, times the volume here, giving us that mass. And finally, moles are going to be this mass divided by the MR, which is 92, if you can see here, giving us 13 moles as the answer. Then in part D, they say polyethanol is made from a polymer intermediate rather than by polymerization, as ethanol is unstable. The polymer intermediate is prepared from a monomer X. When 1 mole of X is burned in excess oxygen, 95.6 decimeters cubed of carbon dioxide at room temperature and pressure, and 54.1 gram of water are formed. The infrared spectrum for the monomer is shown. We can see this here, and there are peaks P and Q. The others are in the fingerprint region. They say use the information to deduce the display structure of the monomer of the polymer intermediate. You must show your working and quote the relevant wave number ranges from your data booklet. So when we see there is this peak P, which I saw about 1735, 1740, this could be an ester or an aldehyde, CO for ester or aldehyde. And there is peak Q, which is about 1640 due to a carbon-carbon double bond, like in alkenes. So I used this information here to find the number of moles. For carbon dioxide, we have the volume of gas given and the molar volume. I got 3.98, which is roughly 4 mole. Since each mole of carbon dioxide has 1 mole of carbon, it means the moles of carbon are actually 4 moles. And for water, it's mass divided by 18, so we got 3 moles. Since each water has 2 hydrogens, it means the moles of hydrogen are 6. So from the wave numbers, like I already wrote, the peak at 1740 per centimeter is due to the carbon oxygen in the ester or aldehyde. You can say 1740. And then the peak at 1645 or 1640 around there is due to the carbon-carbon double bond in the alkene. So my structure is going to be this. Now, there were 2 possible because I said aldehyde, but when you look at the wave number range of the aldehyde, it's a little bit 120, 140. This is way a little bit closer to an ester. And also in the formation of polyethanol, usually esters are used. So that's why I went with this as my answer. And in part E, some hospitals use polyethanol laundry bags instead of reusable washable polyester or nylon bags. State 2 advantages of using soluble polyethanol laundry bags. They are soluble, so it reduces the risk of contamination in the hospitals or even with people who work in the laundry areas. There is also no need to wash, dry, and disinfect the bags. You just use it once, and that is easier. So this brings us to the end of question 19, as well as to the end of the whole paper. Thank you for being with us. Do not forget to subscribe. See you in the next video. Bye-bye.